now that you've got your mental juices going, okay? So you've been thinking for a little bit. So now we can dive into a new topic. So we're going to talk about circular motion. So lots of examples. Here's one right here. So each particle in this meter stick is moving along a circular path. Okay, each particle. Some of them they're all different. This particle up here is a little different than the one down there, right? The planets move around the sun in pretty close to a circular orbit. The moon going around the Earth is close to a circular orbit. When you drive and you go around a curve, that curve can be a circular orbit. Okay, so there's lots of examples where knowing how to handle circular motion is important. Now there are two key results, and that is that the acceleration toward the center is the centripetal acceleration, v squared, over r. R is the radius, and this is called centripetal acceleration. Let's hear you say that. Everybody say centripetal acceleration. If the particle is speeding up or slowing down, there's also a tangential acceleration, and that's given by the time derivative, the rate of change of the speed. So if it's speeding up, you have a tangential acceleration slowing down. So in this example here, we have both centripetal acceleration and tangential acceleration. And we'll talk about that a little more later. So here are the results. Now let's prove them. We're going to prove those results, those two results. This is what you need to know, but let's see where it comes from. There's a derivation in the text. I'm going to do a different derivation. I'm going to do one a little more mathematical. All right? How many people know how to take the derivative of a sine or cosine? Here's the derivation. So we're going to start out with a picture. It's always good. Here's our picture. Here's the particle, and we'll draw a line like that, and we'll call this theta. The angle that the particle makes, that this line makes with the horizontal axis. This is y, this is x. All right? So if I have a vector representing this particle, r, I say it's at x comma y. Is that clear? That's the vector representing the position. Now I'm going to write down those components. This is the radius of the circle, r. What would the x component be? R times what? Cosine theta. Good. And the y component be r sine theta. All right. Now I'm going to use a particular kind of notation to make it clear. When I put a dot on top of a letter, that means the time derivative. How many people have seen this? Nobody. Very few. All right. This will make it look easier, simpler to read. And if I have two dots, then we say that's the second derivative, like that. So our goal is to find the first derivative and then the second derivative of this vector, and to see what we get. Okay? It's pretty straightforward. But of course, you need to know how to take the derivative of a sine or a cosine. All right, so let's take the first derivative. All right, we'll do that over here. X dot. So I'm taking a derivative of this. Does r depend on time? No. So r is a constant, so we can just leave it there. Now we have to take the derivative of the cosine of theta. What's the derivative of the cosine? Minus the sine. So I'll put the sine there, and then I write sine theta. Is that the answer? Am I done? Not quite. Because I'm not taking the derivative with respect to theta. I'm taking the derivative with respect to time. So you add in, you multiply this times theta dot. So it's minus r sine theta. Then you have to take the derivative of what is inside the cosine. All right? So this is no different. If I had something like this, let's say y equals this. How do I take dy dx? I take 2 times dx plus 5, but then I have to take the derivative of what's here. What's the derivative of this? 2. And so that's my answer. It's the same thing I'm doing here, right? I take the derivative of the function, and then because the argument of the function, theta, is not time, I have to take its derivative also, and I multiply it. All right, everybody with me? So all you need to know about trig derivatives is the derivative of sine is the cosine, and the derivative of the cosine is minus the sine. Okay? So if you don't know that, just remember it's useful. Okay? All right, now let's take the derivative of y. So it's the same kind of thing. What's the derivative of the sine? Cosine. And then, just as before, I have theta dot. Okay. So this is my velocity v, just given by that. Now let's find the acceleration. So we're going to take another derivative of each of these. So let's see what happens to x double dot. Derivative of r, we don't have to worry about. R is a constant. Derivative of sine is cosine. So I have minus r cosine theta. But then, because I have to take the derivative of what's inside, I get another theta dot. So I get theta dot squared, because I take the derivative of the argument, and then I multiply by the derivative of the argument with respect to time. Am I done? Is this the answer? I'll give you a hint. I am not done. What did I not do? What has to be done? Remember, I took the derivative of this. I took the derivative of this. What was that? I have to take the derivative of this. So what do? I write minus r sine theta, theta, and I take the derivative of this is just the second derivative, 2 dots. All right? All right, now, to make sure you're listening, I want everybody in the room to do y double dot. So write down what y double dot is. All right? Just follow the same procedure. So I'm taking a second derivative, I'm taking the derivative of this. So we have minus r sine theta, theta dot squared, and then plus r cosine theta, theta double dot. Okay? Maybe I'll put a little parentheses around here. Just so you know, this is not inside the cosine. That's not inside the sine. All right. Now, let's kind of see what this means. Looks kind of complicated. All right? So this is my acceleration. And it's x double dot comma y double dot. Now let's see if we can write it in terms of something else. Notice this. You see I have r cosine theta times minus r theta dot squared. And here I have r sine theta times that. So this first part is equal to minus theta dot squared times the vector r. Did I do that right? Yeah. So these two terms are just equal to minus theta dot squared times this. Everybody agree? What about these two terms? Can anyone see what they might equal? See what these two terms equal. These two over here, do they equal something related to this? So what do you see? It's proportional to the velocity. But what goes in front? Theta double dot. Is that enough? Over theta dot. Very good. All right. So that's the answer. Now let's look at this. This term is minus the direction of r. So it's toward the center. Just like this. All right? And we're going to make that look like this in a minute. This term is along the velocity. That is the tangential acceleration. And I'm going to show you that it's actually, this is related to the dv dt. All right, so let's see how that works. In order to make this a little simpler and to give it a little more physical meaning, I want to find the speed v. All right, so what that is equal to is the square root of x dot squared plus y dot squared. Everybody okay with that? The Pythagorean theorem. All right, and then I put in what that is. I have minus r sine theta, theta dot, quantity squared, plus r cosine theta, theta dot, quantity squared. All right, everybody good with that? Now notice, each term has an r squared and a theta dot squared, and then I take the square root. So I can factor that out. So I get r theta dot, and what's left is the sine of theta squared plus the cosine theta squared. What is this? 1. Sine squared plus cosine squared is 1. So we get that this is r theta dot. And we give that a new name. Theta dot is called omega. All right? So this is omega. And it's called the angular velocity. What are the units of omega? What is its dimensions per time? Radians per second. Radians per second is what it is, okay? I mean, we could do it in degrees per second or radians per hour or whatever, but most of the time it'll be radians per second. If you have it in some other units, try and convert it to that. All right? So we have this nice result that V equals R omega. Okay? So I'm going to change my acceleration with that notation. So I have A equals minus theta dot now is omega squared times R plus theta dot V, theta double dot V over omega. And then I can simplify further. Omega squared from here is V squared over R squared. And so I get minus V over R squared R plus theta double dot V over omega. All right? So notice this. What is the magnitude of this? All right, so I want the magnitude of this term here. What's the magnitude of R? The vector R. What's its magnitude? It's just R. It's just the radius of the circle. So AC is V squared over R squared times R, or V squared over R. That's the magnitude of the acceleration in this towards the center, just like I told you in the beginning. Okay? Everybody good with that? Now we have to do something with theta double dot. So theta double dot is equal to omega dot, and we call that alpha. This is the angular acceleration, right? So we have the angular acceleration. So then I can put that in for the magnitude of the tangential acceleration. T is the magnitude of theta double dot V omega. All right. So that's equal to alpha. What's the magnitude of V? It's just V. All right. And then we have over omega. But omega is V over R. So we get R alpha. So the tangential acceleration is R times alpha. This is equal to dV dt. It's equal to dV dt. The change in the speed with respect to time. So we get that this is the tangential acceleration. How can I say that? V is R omega. I take another derivative, and I get R d omega dt, so I get dV dt. Just comes from this again. Okay. So if alpha is constant, then we can use our constant acceleration formulas from before. And so we get theta equals theta 0 plus omega 0 t plus 1/2 alpha t squared. Get omega equals omega 0 plus alpha t. And we get omega squared equals omega 0 squared plus 2 alpha theta minus theta 0. All right? The same as before. The derivation of that follows the exact same strategy as before. Right? You set alpha equals a constant, and then you find two antiderivatives to get the result. All right? So that's something you should know. All right? Then one last thing that's useful. Sometimes instead of using omega, we use two other concepts. The period, which is the time it takes to go around once, and the frequency is how many revolutions per second. The period times omega So this is angles per second times the period. How many angles do you go per second in a period? If you go around a whole period, how much does theta change? 2 pi. So you just get this result. All right, so that's how you relate the period to what we've had. And then the last result is that f, the frequency, is 1 over t. So this is the frequency. All right, so hopefully you've seen this before. OK, so we have a bead that's rotating on a circle. OK, and to make it a little simpler, that circle is horizontal. OK, so the bead's going around like this. OK, it's like on a hoop, and the bead is on it. But there's one slight twist to it. There's friction. All right? So there's friction on the bead. It starts out, let's say, going like that. All right? Now I'm going to draw 4 vectors, and I'm going to ask you questions related to that. So that's one vector. I'm going to call that A. That's another vector. I'll call that B. That's another vector, C. And that's another vector, D. All right? So everybody see the 4 vectors. So the first question is, I'll be simple. So which is the direction? A, B, C, or D? D. Any disagreement? Now we're going to ask, what is the direction of the centripetal acceleration? A, towards the center. All right, now we're going to get a little tougher. Is there, and if there is, which direction is the tangential acceleration? A, B, C, or D?
You mean the circular motion, in a circular motion?
It's going in a circle, but there's a tangential acceleration. There's friction. It's moving in this direction. So is the tangential acceleration A, in the direction of A, B, C, or D? OK. Good. Why?
Because if the acceleration is in the same direction of the velocity, I think it would, the particle wouldn't move like a circle.
No, he's always on a circle. If it is in the same direction as the velocity, it speeds up. It goes faster.
Yeah, which, I mean, it's the same direction with D. It's total acceleration, the direction of the total acceleration.
No, not total, just tangential acceleration we're talking about. The tangential acceleration is in the C direction because it's slowing down. Yeah.
What I mean is, if the particle needs to be moved in a circle orbit,
yeah,
its acceleration must be put to the central.
No. No.
Circle.
Even if it's in a circle. Only the centripetal part of the acceleration is towards the center. But the total acceleration is not towards the center. There's 2 accelerations. One towards the center, that's the centripetal, and one tangential, that is the tangential acceleration, because it's slowing down. Okay. So I'm going to, yeah, you have a further question on that? It's still going in a circle. Okay.
So the circle, the orbit is that you fix particle?
Yeah.
Or you,
It's a circle. It can't go outside the circle because it's fixed on this circle. It's a
you
bead
fix
going
it
on.
first.
That's right. So it can't go out of the circle. Okay. All right, now I'm going to ask a related question. All right? So we talked about tangential. We talked about centripetal. What is the direction of the total acceleration? The total acceleration. Is it A, B, C, D, or something else? Between A and D. This way? Close, not quite. Because remember, the tangential acceleration is along C. So if I add this vector to this, I get a vector like that. So that's the total acceleration. All right? So the centripetal is towards the center, A. The tangential is against the velocity because it's slowing down, that's C. And the total is the sum of the vector going towards A and towards C, and that would be between A and C. So I have this particle going around on this circle. There's friction, sliding friction, that's causing it to slow down. And we know that sliding friction, the amount of the sliding friction is proportional to what other force? A normal force. Which direction is the normal force on this diagram? No, actually, it's going around like this. It's not in the z direction. Remember, there is a normal force in the z direction. That's true. Okay, that's a good point. But there's also another normal force. Good point. There's a z direction normal force that balances gravity. But there's another normal force. Which direction is that other normal force? A, B, C, or D? Yell it out. What? C. There's a normal force in the C direction? The answer is A. Why? Now, why is it A? There's a centripetal acceleration in this direction. There's got to be a force in that direction to produce that centripetal acceleration. That's Newton's second law. F equals ma. If there's no F, there can't be an A. Since there is an A towards the center, there must be an F. And the only possible F is the normal force. So that normal force is towards the center of the circle. All right. Now, so we have that normal force towards the center. We have this particle going around. Due to friction, it's slowing down. Can we use these equations to find the motion of the particle? When do we use that? When the angular acceleration is what? Constant. If the angular acceleration is constant, what does that tell us about the force in the tangential direction? It also must be constant, right? If the tangential acceleration is constant, the force in that direction must be constant. Everybody agree with that? The force in the tangential direction is friction, sliding friction. And that is due to the coefficient of friction times what? The normal force. Is the normal force constant? Really? The normal force is towards the center. It's given by m times what? Which acceleration? The centripetal acceleration. Here's the centripetal acceleration. Is r a constant? Yes. Is v a constant? No. Is ac a constant? Is n a constant? The normal force, is that a constant? No. So is the tangential acceleration constant? No. No, no, no. So you cannot use this. You can't use it because that assumes a constant acceleration in that direction. All right? So this is a kind of reasoning. This is pretty advanced reasoning for this level course. It really is. I think you guys are smart enough that you can figure it out. All right, now we're going to do another example. See if you learned anything. All right, we're going to do a pendulum. We have a pendulum. So the pendulum has a mass at the end, and it oscillates between this point and this point. So it's going from there to there. And I'm going to consider 3 points, A, B, C, D, and E. All right, here's my question. I'm going to pick a point, and I'm going to ask you, is there an centripetal acceleration? Is there only a centripetal acceleration? Only a tangential acceleration? Or both? Or neither? So either there's no acceleration, there's both tangential and centripetal, there's only a centripetal, only tangential. Okay, everybody know what the possible choices are. So let's start with A, the point A. So that's the point. This is my pendulum. That's the point right now. So right at the end is point A. All right, everybody understand what point we're talking about? Okay, so here's your choices. Only centripetal, only tangential, both, neither. What do you think? At this point A. All right, she says both. Why? Let me ask you a question. Here's the centripetal acceleration, right? What is the speed at this point A? 0. So what does that say about this? 0. All right. Is there a tangential acceleration? Yes. Can you tell me why? Why do you think? If its velocity is 0 here and there's no acceleration, what does that mean? It sticks there. It would be like this. Is it doing that? No. So there's got to be a tangential acceleration. Okay? All right. Now you guys should be able to figure out the rest. All right, let's see what you can think of. All right. So we're going to go along to B. So at B, is there tangential, centripetal, neither, both? Both. Why?
Because of the gravity.
So what does gravity tell me?
It's pulling the object down.
Yeah, but it's not going down. It's going in a circle.
You can break out the gravity.
Ah, okay. All right. Can you do it without thinking about forces? Just about the motion? For example, is the velocity 0? Speed 0? No. So that means there's got to be a centripetal acceleration. Is the speed changing? Yes. So that means there's a tangential accelerator. That's all it is. You don't need to think about forces, at least for B. OK? See that? Good. All right, let's do C. So what do you think? Centripetal, tangential, both, neither. Here's where it is useful to think about forces. Because at C, there is no force in this direction along the motion. There's gravity down, pulling it down, and the tension from the string pulling it up. So at C, there is no tangential, but there is a centripetal. So at A, it's only tangential. At B, it's both. At C, it's only centripetal. At D, what do you think? Everybody yell it out. Both. And what about E? Only tangential. Good. Okay? See how this works? So you can use reasoning. And there are a lot of things you can pull from to try and get the answer. So I'm going to do one of my favorite problems. So we're going to use the same strategy that you should have used on the quiz today, except with circular motion, there's two major differences. One is we don't use x and y as our coordinates. We use a different axis. If this is our circle, and this is our point, we imagine we're at the mass, and one axis is this way, the r-axis, and the other axis is the t-axis. And then we could also have a z-axis in some cases. OK? Now I'm going to show you an example of that. All right? So there's an r, a t, and a z-axis. So what you do is you follow the same strategy. You draw a picture. You do a free body diagram. You break it up, right, Newton's second law, into the r, t, and z directions. OK? Then you put in what you know. If it's in the r direction, you put in this for the acceleration. OK? If it's not speeding up or slowing down, you can put in the tangential acceleration as 0, and then whatever's going on in the z direction. And then you put in for what you know about forces. All right. So here's the problem we're going to look at. It's an amusement park problem. I don't know if you've ever seen this. You're in a circular room. All the people, they stand at the end of the room with their back against the wall. Then the circular room starts to move. It moves around with a certain velocity. It goes faster and faster. And so it's keep going fast. And then here's the scary part. The floor disappears. The floor disappears, but the people do not fall. How does that work? There's friction, but how? How fast do you have to move? So let's figure this out. OK? So here's the basic idea. Here's our room. It's rotating around like this. OK? Here's the person. OK. Here's the r direction. The t direction is into or out of the blackboard. And then this is the z direction. OK? All right, let's figure out, draw a free body diagram. What are the forces on this particle? So give me a force. Gravity. There's gravity down. mg. What other force? What was that? Normal force. Which direction is that? Towards the center. Good. So there's a normal force towards the center. Any other forces? Friction. Which way is that? Up. Good. All right. And since it's sliding friction, it goes by mu times n. Okay? So we only have two directions to worry about. In the r direction, what do we have for F equals ma? What do we have in the r direction? We have the normal force equals m. And this is centripetal acceleration, right? It's going around in a circle. mv squared over the radius of the circle. Mu times n minus mg. What is the acceleration in the z direction? Up and down. What is it? 0. Right? So we get n mg over mu. Stick that in there. And we get mv squared over r equals mg over mu. All right? So your velocity, the speed at which this goes around, has to be fast enough so that this works. Okay? Mu, the maximum mu would be mu sub s. The friction force will actually adjust itself depending on what's needed. But there's a maximum it could give. And so what they do at these amusement parks, has anyone ever been in this ride? All right. So one of the things they do to make the friction force bigger is there's like a carpet on the wall to make it more friction in order for it to work. Okay? So this is the strategy that people use.